So that's the ultimate goal of most of the neuroscientists, to have that extension, so that there will be synapses, growth, differentiation, and neuron does its function. When they have any of these, they go for the therapy, all the good stuff. By the end, when they get out of the rehab, only less than 1% of them get the full recovery. So those facts are alarming when we talk about the neurological disorder. This slide kind of explains my project. So this one is an injured neuron. We have almost 50 key compound that has been used to gain that local signaling thing back, and they have phenotypically screened all those compounds. Most of them affect this one over here. That's a mevalonic pathway. Why do I care about mevalonic pathway? Because you see over there that protein prenylation, that's where my GTPases are. That's why I care about that pathway. To find out how all these, I have been doing that. So to find out how all these compounds react, talk to each other, activate, deactivate different pathways, it will be very important to come up with some pharmacological inhibitor or some drug, so that we can have extensions over here, and neurites can outgrow. They can form all those good connectivity, all those synapses, and life is good. That's the ultimate global goal of most of the neuroscientists working in the field. This is for one of the neurodegenerative disease, ALS. Now, let's talk about my protein, RHO-GTPases. When we talk about RHO-GTPases, the most studied one are RHO-A, RAC1, and CDC42. CDC42. They are cytosolic protein, and they need to be prenylated. Then they go to the membrane, and then they tell other effector, other protein what to do, and they do tons of work. When life is good, RHO-GTPases are active. They have so many functions, from cell growth to differentiation, motility to gene transcription, and very important and very dear to me, rearrangement of actin cytoskeleton. All these neurodegenerative diseases we talked about, most of them have some implication on this RHO-GTPases. That's where my protein comes in picture. Now, how does this protein actually get into active, inactive, membrane targeting, all that? When RHO-GTPases are GDP bound, they are inactive. When they are GTP bound, they are active. That's why we call it molecular switches. So they go back and forth from GDP to GTP binding, and that's how they get active. Now, why do we care about gerenyl gerenylation? What is gerenyl gerenylation? This is a post-translational modification. Gerenyl gerenylation is addition of lipid moiety to the cysteine of the protein that helps it to get to membrane. There is another lipid moiety that gets attached, that is farnesylation. So it is 15 carbon moiety. This one, gerenyl gerenylation, is 20. Together we call it prenylation. So when we stop this gerenyl gerenylation, we stop this protein to get membrane targeted. So when it is gerenyl gerenylated, it goes to the membrane and it does the function. When we have non-gerenyl gerenylated, it won't go to the membrane. Now, if it does not go to the membrane, what it does? That will be my later question. Background of my project. This is the work from previous lab mate, Dr. Jairus Reddy. This was already published one. We are working on that one. It is under revision. So when you see this one, this is the wild type RAC1, and this one is the mutant RAC1. So when I talk about mutant, we stopped getting it geranyl-geranylated. So it is not membrane targeted now. So we stopped it from getting geranyl-geranylated. Same thing over here. We have row A. And then we have this one that is a mutant type. So again, that is not able to go to membrane because they are not geranyl-geranylatable. I would call it wild type and mutant. So to stop that, because it took me just a semester to get that word right. Okay. So by overexpressing row A or RAC1, we are not doing anything to endogenous protein. They are there as it is. And then we this paper particularly already talked about that RAC1 is present in cytosol. And this one that we are working on, that shows row A is also present in nuclear fraction. That's what we are working on. So RAC1 is present in cytosol, row A in membrane and nucleus. So this was all the background. My question was, fine, we have rho GTPase in nucleus, we have rho GTPases in cytosol. How it is affecting the actin cytoskeleton, and if which fraction they are located is doing something to its function. That was my overall testable statement that guided my dissertation work. The three aims of my project was to see overexpressing row A and RAC1 if it decreases the actin content in growth cone. In a minute, I'll tell you what is growth cone, filopodia and lamellopodia. Second one was to see by overexpressing RAC1 and row A, what are the pathways involved? Is it going via depolymerizing, that is covalent pathway, or it is going via polymerizing pathway, that is JNK and ERK, and also actin nucleator molecules, that is via WAVE and ARP. The third one was to see how these serine kinase pathways help in actin nucleation. These were the three aims that I checked for my dissertation work, and if I can have a better view, this is actually what it is. So my aim one will be to check actin cytoskeleton, how overexpressing row A and RAC1 increase or decrease, basically decrease the actin cytoskeleton. Actin content, my bad. My aim two will be to check for all those three pathways, JNK, ERK, WAVE and ARP, for both row and RAC. My aim three will be to see if there is any crosstalk between all those pathways. For that, we incorporated pharmacological inhibitor to see if there is any crosstalk or not. Let's go for aim one. So in aim one, we will see how overexpressing my row A and RAC1 decrease the actin content. This is the growth cone I was talking to you about. This is the growth cone, and they are loaded with actin filament. All those green structure that you see, those are actin filament. This one over here, just underneath those projections, those are lamellopodia, and this one is filopodia. These are the reason that allows neuron to grow forward and then do all the functions like connection, different connections, synapses, and all that good stuff. And on figure B, if you see, this red one are microtubule and the green stained one is actin filament. How did I proceed with this aim? The very first one I did was Western blot analysis. So I have done this for my throughout the presentation. You will see this. The B35 neuroblastoma cells were transfected with row A and RAC1. Why I chose neuroblastoma cells? They are easy to transfect and they have so many neurites to study. So it is easier to study all those extensions in them. The neuroblastoma cells were transfected and we analyzed it via Western blot. We didn't see any significant difference over there. This bar over here represent they were normalized with untransfected one. And throughout the presentation, you will see all my conditions are compared with the EMGFE, that's my control. So by overexpressing row A, we didn't see any significant difference between wild type or the mutant type over here. Is it true for different fractions now? Because I already showed you the slide about row GTPases where they are present in different fractions of the cell. So is it true for the different fractions? This one over here is cytosolic fraction. This one is cytoskeleton fraction. On the Western blot diagram, F1 represents cytosol, F4 represents cytoskeleton. We didn't see any significant difference by expressing wild type or mutant over here in cytosolic, cytosol or in cytoskeleton. We didn't see any significant difference. You might notice my y-axis over here and my y-axis over here is different. Because we have more actin filament content in cytoskeleton than in cytosolic fraction. That's why if I would have gone with the 30 over here, you won't be able to see any of those bar over here. That's why I have to have two different y-axis in both of them. So this was done by phalloidin stain, and these are the growth cones. Where you see those little extensions, phalloidin actually stained the actin filament, and that was the reason I used phalloidin to see the exact the actin filament content in the growth cone. For this purpose, growth cone was identified, and then we checked if it has any difference by overexpressing row A. We didn't see any significant difference by overexpressing wild type or mutant form of row A. This is all from neuroblastoma cell, how it is getting affected in rat cortical neuron. First of all, it is very hard to transfect the primary cell line. We achieved almost 20 or 25% of transfection. That's it. So the only thing we can study is by staining. So we chose phalloidin stain. And again, when we identified our growth cone, did the numbers, we didn't see any significant difference by overexpressing row A or RAC1. This was all for row A. How is it gonna affect, or how is RAC1 gonna affect this overall process? Same thing, by overexpressing RAC1 in whole cell lysate of neuroblastoma cell, we didn't see any significant difference. Is it true in other fractions? We did see difference over here. By overexpressing wild type RAC1, the actin content was increased. Not in the cytosolic fraction though, just in the cytoskeleton fraction. For this one, we are taking the cell lysate or the fraction of different fractions. So it is covering up all the fraction. What about in the growth cone? For that, phalloidin stain again. We did see the difference over here, significant difference. By overexpressing wild type, actin filament content was increased by overexpressing RAC1. Is it true in cortical neuron now? So this was all about neuroblastoma cells in RAC1. Is it true in cortical neuron now? We didn't see any difference in RAC cortical neuron. There was no significant difference. What are the conclusions from aim 1? By overexpressing row A, we didn't see any difference in active filament content in cytosolic or cytoskeleton fraction. And same thing in rat cortical neuron. We didn't see any significant difference by overexpressing RAT1 or row A in rat cortical neuron. But by overexpressing RAT1, we see significant difference in cytoskeleton fractions. So that was the only difference we found after overexpressing row A and RAT1. That was all about aim 1. Aim 2. This is where all these pathways I told you we're going to talk about. I know this is a busy slide, sorry about that. I'll walk you through with this one. These are again neuroblastoma cells transfected with row A. The first one on over here, these are all from whole cell lysate. Second one over here is from cytosolic fraction, and third one over here is from membrane fraction. For this one, over here in the Western blots panel, you see the top one is ERK and bottom one is phospho-ERK. Why do I care about phospho-ERK and ERK? Because ERK is active when it is phosphorylated. To find the active ERK, we have to probe it with both phospho-ERK and ERK to find out the total amount of active ERK. Same thing across the board. That is for all three. When we overexpressed row A in whole cell lysate, we don't see any significant difference. Same thing over here in membrane fraction, we didn't see any significant difference. But right over here, you all can see that star. We do have a significant difference over there. So by overexpressing row A in cytosolic fraction, we decreased the active ERK. The mutant type increased the active ERK. Okay. Now, to make sure I had efficient separation of the fractions, we did the marker plot over here. So calnexin is only present in cytosolic and GABA A beta 2 is present in membrane fraction. That was just to have a efficient separation of cytosolic and membrane fraction. Is it true in the growth cone? The first panel over here represents DAPI, second one for GFP, third one for ERK, and fourth one is for phospho-ERK. Again, growth cone were identified. We have different intensity over here, and we did see the significant difference by overexpressing row A. So active ERK was increased by overexpressing row A. In mutant type. Junk. Same pattern over here. To find the total junk, we have to do the phospho junk and junk, that is over here across the board. By overexpressing row A, we didn't see any change. Be it in whole cell lysate, be it in cytosolic fraction, be it in membrane fraction. The active junk was not changed across the board. No effect on junk from overexpression of row A. Now, it is from Western blot analysis. How about the confocal? I have tried to answer all these questions by two techniques to be on the safe side. We are getting the same result from two techniques. When over here, the first one again, DAPI, second one transfection or GFP, third one junk, fourth one phospho junk. We didn't see any significant difference over here in the growth cone again by overexpressing row A in junk, active junk. No difference. Western blot over here, but these are actually pull down acids. So I pulled down wave and then probed it for R to see how they are interacting, wave and R. Because wave and R are downstream of rho A and they also help in actin polymerization. So that's why I chose this actin complex nucleator molecule. By overexpressing rho A, this one over here, we didn't see any difference in wave R associated in the whole cell lysate. No difference in the membrane fraction, but we did see the decreased wave and R by overexpressing wild type rho A. And all these Western blot over here, you see, they were also probed for wave to see if there is any change across the board. We didn't find any change, so that's why I didn't put it over here, but that was my control to see if they are changing, so we also probed it with wave. We didn't see any change. That's why we don't have that over here. Now, for all the previous confocal images that you see, we didn't have this one. Over here, you see those are checking for the co-localization. All those arrows are showing the co-localization. The first one again, nucleus, GFP, wave, R, and those one are from the co-localized one. By overexpressing rho A, we decreased the wave and R association by wild type. That was from the growth cone of the neuroblastoma cells. This is again from all the rho A. How it is getting changed and what are the other, what out of all these three effectors that we checked are junk, wave, and R, how they are getting affected by RAC1? That will be the next question. Same pattern, following the same pattern, we did first with whole cell lysate, cytosolic fraction, and membrane fraction. Across the board, we don't see any change by overexpressing RAC1. No change in the active ERK by overexpressing RAC1. Is it true from the growth cone? Yes, it is. Same thing, GAPP, GFP, ERK, phospho-ERK, and over here, no significant difference by overexpressing RAC1 in the growth cone. How about on the junk? When we overexpressed RAC1, we do see change over here. These two over here, you see? We do see significant difference by overexpressing wild type RAC1 in the cytosolic fraction. We don't see any change in whole cell lysate or membrane fraction.
Is it the mutant?
Yeah, sorry, mutant here. Did I say wild type? Oh, sorry. Yeah, okay, my bad, yes. Sorry. By overexpressing mutant. This also go along with the Jay's work where he said that RAC1 is active in cytosol, so maybe it is working via this pathway, one of the pathways involved over there. Is it true by the immunostain? Yeah, over there. There is a significant difference by overexpressing RAC1. Now again, OIP or immunoprecipitation of wave and ARC. So this one was by overexpressing RAC1. RAC1 was immunoprecipitated and probed with ARC to see their association. This is the most interesting one for me because all the plot that I showed you, none of them showed any change in the whole cell lysate. But if you see over here, this tiny star over here, I do see the difference in whole cell lysate by overexpressing RAC1. That's the only one where I got the positive result in the whole cell lysate by overexpressing. Cytosolic fraction, membrane fraction, no change. By overexpressing RAC1, no change in the wave and ARC association. This one on the top, where again, probed with wave, we didn't see any change, so we do not have that dot over here. If anyone interested, I can show you. I have the same across the board. This is again the colocalization study. The first one is with nucleus, second one is transfection, third one is wave, fourth one is ARP, and the fifth one is merged with all of them, and the arrow represents the colocalization. By overexpressing RAC1, we didn't see any change in the growth cone of any of those neuroblastoma cells. Conclusion of my aim 2. Overexpression of or I would say mutant Rho A leads to actin polymerization by wave and ARC pathway, and RAC1 leads to actin polymerization by junk and wave pathway. So Rho A is doing actin polymerization by wave and ARC, and RAC1 by junk and wave. It is pretty interesting to see that wave is involved in both of them, Rho and RAC. This one is also interesting because all the previous work we have seen, wave and ARC is downstream of RAC1. All the work that we have seen gone through, it is wave and ARC is downstream of RAC1, not of Rho A. But this again arises the question because there are some researches where they say RAC1 is also activated by Rho A. So that might be heading to that pathway, that Rho A affect RAC1, and because of that, wave and ARC might be talking. Aim 3. Now, aim 3 is talking about all the pharmacological inhibitors to see how they do crosstalk between all these pathways. I'm sorry guys, this is very busy slide again. Wherever you see this negative sign, that shows they didn't have any inhibitor added to it. Whenever you see positive sign, that means inhibitor was added to it. So what we did, we transfected our neuroblastoma cells. Transfection was there for 48 hours, and then using a specific amount of all this inhibitor, we treated all the transfected condition. Had the whole cell lysate, and then probed with all these specific effector over there. Across the board, you see, first one was with ARC, second one was with junk, and third one was with ARC inhibitor. Just by looking, we have not yet analyzed our aim 3 fully. It is in the procedure. Like we have done the work, but we have to sit down, analyze it, take each pathway at a time, and then see what is the crosstalk going on. They're doing something, all that stuff. We have not analyzed this one yet. Just so blot has been done. We have to sit down and then do it. But just by eyeballing and checking it, by inhibiting junk, there is some talk going on in the ARC one, but that is across the board again. And I'm sorry, I need to get a better plot for that one again. Same thing with junk over here. When we have ARC inhibitor, there is again some crosstalk going on over there. What it is, but it is again across the board, we have to figure it out. Over here, by ARC inhibitor, again there is crosstalk between junk. Also with a little bit on the ARC side. This is by overexpressing Rho A. Is it true for RAC1? Same thing over here, ARC inhibition, junk inhibition, ARC inhibition. By inhibiting ARC inhibition, there is again some talk going on with the junk. Junk inhibition, there is like good difference over here. That will be a good thing to sit down and talk about. That will be my discussion portion of the dissertation. On the junk one again, by inhibiting ARP, we see over here, big difference. These are all the questions that I have, and how they are talking, what are the other networking coming in picture will be my discussion portion again. Conclusion of AIM3, as I told you, we have not yet fully analyzed this AIM3. So far, junk inhibition affect the ERK pathway. In case of overexpressed non-journal knowledgeable group A and RAC1, both of them. And I would have all these analyzed hopefully, not hopefully, yes, by my defense. Yes, so I have to analyze it. I have to analyze it, or my committee won't allow me to graduate. Yeah, my bad, sorry. Hopefully by the end of this month, I'll be able to analyze all of this. So this one was my overall pathways that I repeatedly showed you over and over again. This is all the pathways that I came up with, but are they all involved by overexpressing Rho A? Actually not. So by overexpressing Rho A, we have these two pathways that is playing. So these two pathways, and there might be some other different player in between. They might be doing some of this stuff. When I talk about the pathway, I'm checking by my effector, and there are always crosstalk going on in between. There are other effectors that might be playing its role. So there are so much of stuff going on whenever we have pathways to talk about. What about RAC1? So we have again junk, ERK, and wave, and ARP. What are the pathways involved in this one? This one, junk and wave and ARP. Why do I care about this pathway now? This one over here? Fine, we got over here actin cytoskeleton. Once we attain the actin cytoskeleton, we can have all these extension in the growth bone that will allow these neurons to extend or to regrow. That is the slide. We will gain spine density, that's what it is called as. And they will be able to grow and do all these good work of extension, synapses, because if we lose that, that is one of the reasons for so many neurodegenerative diseases. That's the whole goal. And as I told you, that's the ultimate goal of most of the neuroscientists, even the neuroscientists among us. That's the ultimate goal. Big goal, but I'm working on the molecular level. Just my actin pathway, that's what I care about right now. That's the ultimate goal. Maybe before I die, I'll find something. And if that is attained, then Merry Christmas. Okay, now this is the most difficult slide. I won't have been able to stand here, talk about all these Rho GTPases without these people. And thank you for all of you being here today on Friday afternoon. My committee. I'm most scared of Dr. Hansen and Dr. Uphouse, FYI. If I can survive them, I can survive my committee. Dr. Phyllis for awesome suggestions. Dr. Everett, always being my go-to person. Although I belong to Heinz Lab, I never felt like I'm not part of Everett Lab. Always any question from calculation, question, anything.